He developed 4, but
No,
it's
that's
scratched
not
on
true.
off.
You can't push a rope. That's a joke. Just 3, please. He developed a theory describing gravity, and he did a famous prism experiment, which we'll play with prisms here in a few weeks, that showed that white light is composed of many colors. In order to help his scientific investigations, he discovered or developed a new kind of mathematics that we now call
Calculus.
calculus.
Okay,
Yeah.
I can't read mine.
That's okay, and it's not like you guys have taken calculus yet, so calculus shows like how something changes over time instead of where something is at any given instant. In a nutshell, kind of, and more. He was also devoutly religious, and he spent much time studying the Bible. So, and that was pretty normal for scientists of his age, that many, many scientists were Christians. So that's kind of changed a little, and I hope that some of you will go into science and hold tight to your Christian beliefs and shine the light of Jesus for people who are in the field. But you will encounter a lot of making fun of you and, are we filming this?
No.
Thanks,
We are.
everybody.
It says rec. There's like flash.
Oh, it's recording. It is probably working. Okay, so Max. Newton's 3 laws once again.
When an object is in motion or at rest, it tends to stay in motion or at rest until it is acted upon by an outside force. Then the second one is F equals ma. And then the third one is that for every force, there's an equal and opposite force.
Okay, for every force, there's an equal and opposite force. And if you write action instead of force, it's okay. But I just think force is kind of more descriptive. Wow, window is so bright I can see Max's hat and nothing else. It's like hat and bright light. Okay, so Patrick, the tendency of an object to resist changes in velocity is referred to as...
Speed.
Not quite. What's the first law that Newton came up with, sometimes called?
An object in motion,
That one, what do they call it? The law of
inertia.
inertia. Okay, so resisting change in velocity is referred to as inertia. Just like when I flicked the card in the little metal thing, which I hope I gave back to you, did I? I might have stolen your little metal thing.
That was a little piece of chip of the egg.
Oh, no, I actually took a tiny metal thing off your desk.
That's broken
Okay. When I flicked the card, the little metal thing resisted a change in velocity. It had inertia. It went straight down instead of going along with the card. So, when a bomb is dropped from an airplane, the bomb
now. Does not,
hit the ground directly below where the airplane dropped it. Instead, it continues to move
in the direction.
that the plane was moving when the bomb was dropped because of Newton's
Second. First law.
law of motion. So the first law is called the law of inertia, and just like you demonstrated with the wood block, when you run, drop the wood block, it keeps your velocity. When the plane drops the bomb, it keeps the plane's velocity as it falls. It moves forward. It doesn't just go boom. It goes like a nice little parabola kind of shape. Thus, the bomber must drop the bomb before it's over the target, right? If I want to fly by and drop a bomb that's going to hit that marble and I'm flying along, I need to drop the bomb like now, and it will keep flying. And then if I don't change the plane's direction, I'll be directly over it when it blows up. But if I am a smart pilot, I'd probably go that way. And Duchesne, the reason, now it's really dark, the reason that Aristotle, I can't read, made so many mistakes when describing motion is he did not know about the existence of
Friction.
a force that opposes motion, the result of contact between two.
Surfaces.
This force exists because on the atomic scale all surfaces are
Rough.
good. I put bumpy. I'm like, rough is good. This affects how close the molecules can get to one another, which affects how much they are
Attracted.
to each other. the more that they are
Attracted.
to each other, the stronger the frictional force. When this force opposes motion, once the motion has started, we call it...
I don't have an answer for that.
We haven't read that far.
Okay, we haven't read that far. Okay, so we'll talk about that. So that's kinetic friction. And when the thing hasn't started moving yet, then we're talking about static friction. And which one is stronger?
Static friction.
Static friction is stronger. So once again, if we go back to the block, Bethany, when I push on the block, before it starts moving, it has more friction with the table. Once I get it moving, I don't have to push quite as hard to keep it moving. Because, like you think, you can see the table's bumpy, right? The wood looks smooth, but you know if we put it under a microscope, we'd see like bumps and grooves, and it wouldn't be smooth at all. Okay, so here's kind of the analogy. If you're riding your bike down a sidewalk and there's a pothole, or maybe the road, and there's a pothole, right? What happens if you're going really slow on that bike and you get to that pothole?
You're gonna fall into it.
Yep, bam, your tire just goes right down in there. What happens if you go to the pothole and you're going really fast?
We go over it.
Yeah, you just like go right over it. So think of the surfaces as having a lot of potholes, right? And they don't really interact with each other once the thing is really moving. But they definitely interact with each other a lot more when the thing isn't moving or is moving really slowly. It's just similar to just hitting that pothole. Of course, it stops you a lot more when you fall into the pothole going slow and then have to get out than it does if you just zoom over it. You guys know from experience, if you are pushing a really heavy object, like my lab bin, when I start pulling, right, it takes a lot of force to get it going. Once I get it going, it's a lot easier to keep it moving. If I have to stop, then I have to start it all over again. Anyone who has moved something that's really heavy knows that once you get it going, you do not want to let it stop. You've got to keep the thing going, or else you'll have to do all that extra force to get it moving again. Much easier to keep something going than to get it started. That is the difference. Static frictional force is much bigger than kinetic friction. You have to overcome a big force of friction to get something moving, but to keep it moving is less. And it's the bumps and grooves and the crashing with the pothole are one part of the thing that causes friction, and the other part is electrostatic attraction. You guys have seen a little bit of that with getting a balloon all charged up, and we can maybe attract some pieces of paper, pull our hair and attract it, stick the balloon to the wall, right? Well, when something has a charge and something has the same charge, they repel. When two things have opposite charges, they attract. And there are charges on every surface all the time. Some repel, some attract. And those forces lend themselves to causing friction also, which I don't think your book talks about at all, but that's kind of where friction comes from. Potholes and electrostatic forces. So, let's see. Math. The math on this test, I have a quest for you guys that I wasn't going to hand out this week, but I think I will. And we will... Did I already hand it out? No. Lay it somewhere. Anybody see the quest? We need a quest to the quest. Here we go. No. Pile of papers laying around anywhere. No. Well, let's see. I lost the quest. Okay, well, let's look at the math on the study guide or summary. I seriously cannot find the question. Okay, so we've talked about friction, we've talked about F equals ma a little bit. Looks like, I think I talked about that. Okay, well, let's look at study guide problem 9. A child is pushing her toy across the room with a constant velocity to the east. I don't have to get that thing moving then. So here's my toy. I'm pushing it with a constant velocity, right? It's not speeding up or slowing down. Its velocity is constant, and it's going east, which let's pretend that is. The static frictional force between the toy and the floor is 15 newtons, and the kinetic frictional force is 10 newtons. Which one am I exerting if the toy is moving? Anyone want to take a guess?
10.
The 10. Okay, because kinetic, you guys know kinetic means in motion. Static, like stationary. Think. The two words are very similar. Static friction is the larger of the two, and the object is stationary. Is it ARY or ERY, folks?
ARY.
Probably. I can't remember. Kinetic. Kinetic friction is always smaller, and the object already has to be moving. Static and stationary have the same root word. Kinetic means in motion. So if I'm already pushing this object and it's already moving, then the frictional force between it and the table is the kinetic frictional force. If it's not yet moving and I start pushing on it until I actually get it to move while it's still stationary, it's experiencing a larger static frictional force. So since the child is already getting her toy to move, the frictional force is 10 newtons. One note about friction and forces, just like velocity is a vector quantity and acceleration is a vector quantity, and you need to include direction with those, force is also a vector quantity. So anytime you give an answer that's a force, you need to write the direction. Now in this one, it just asks if the force is 10 newtons or 15 newtons. And if you just said 10 newtons, that would be fine. But forces are vectors, and they need directional information. So here's the question. What would the direction of the frictional force be if I'm pushing that thing east?
It's going to be to the west.
Exactly. Why?
Because it's pushing against the direction.
Right. Friction opposes motion, and that's a rule. You can always count on that rule. So friction opposes motion. So if the motion is going west, the frictional force is going east. Always in the opposite direction of motion. Air resistance is the same. Do you all know where the energy that it steals? Because, right, if there were no friction, I'd be moving this thing faster, right? With the same amount of force. So where does all that energy that friction steals go? Heat. Good. So when the two surfaces are in contact, that brick of wood and that table, when they slide, and whatever friction takes becomes heat. They rub against each other, and the molecules that are interacting get warmer. So the table heats up a tiny bit, and the brick heats up a tiny bit when I'm pushing it. You can definitely experience that when you take your two hands, you rub them together, the friction creates heat, and you can feel it, right? And like we talked about the other day, air resistance, when I just whack air molecules like this, it slows my arm down because I'm hitting air molecules, and it heats up the air molecules. Friction and air resistance, all of the energy that's lost to them goes to creating heat in something. I don't know if you need to know that, but just an interesting point about friction. Let's see. So look at number 10 on the study guide. A father is trying to teach his child to ice skate. So anytime we need to do problems where we want to ignore friction, we don't have a lot of options in this world. There are not many frictionless surfaces, and so when we're ignoring friction, we go for ice. So when you're on ice, probably you're going for a problem ignoring friction. Ice is very slick. there's not much electrostatic interaction, there's not much bump and groove kind of interaction. You can slide on ice. It reduces friction significantly enough that we can ignore it. As the child stands still, the father pushes him forward with an acceleration of 2.0 meters per second squared north. So anytime I have a problem like this, I just start writing down what I know. So if it says acceleration, I'm going to write down A equals, and it says 2.0 meters per second squared. 2.0 meters per second squared north. Actually, N means Newton, so maybe I'll write north out. And then it says, if the child's mass is 20 kilograms, the mass, so look here, we've got mass and acceleration, 20 kilograms. What is the force with which the father is pushing the child? Since you're on ice, you can ignore friction. So, if I want to know the force, and I know the mass and the acceleration, what should I do? Shane?
Multiply them.
Multiply them. Okay, so what I want you to do, always write down the information you know, then write your equation. Your equation in this case is F equals MA. Write your equation on every problem. Even if you just used it in the last problem, write your equation down. I even give partial credit. If you can't get any further than write the equation down, you'll still get some credit for knowing that's the right equation to use. So I just plug in. I'll just do it here. So mass is 20 kilograms. Acceleration is 2.0 meters per second squared. So what happens when I multiply 20 times 2?
It's 40.
It's 40. And now what about my units? Look at these crazy units. Kilogram times meter divided by second squared. Wow, what's that all about? Shane?
Isn't that the Newton?
That is a Newton. So 40 kilogram meter per second squared equals 40 newtons. Because this complicated unit, the kilogram meter per second squared, is a Newton. Force is mass times acceleration. You've got a mass unit, and then meters per second squared is an acceleration unit. So that's a force unit, and the kilogram meter per second squared is a Newton. You could make force units out of anything. You could do, well, do you guys know what mass is for us when we use English units?
Pounds.
No.
Or ounces.
Pounds is actually the force
Just
unit
slugs,
for us.
right?
Slugs. Isn't that crazy? Slugs. Slugs times, and what do we measure in? Not meters, but
Centimeters.
slug foot. And we still use seconds, so that's good. The slug foot per second squared is a pound. So, slug is our mass unit, pound is our force unit. So if you tell me how many pounds something is, that's a force, then you're supposed to tell me a direction. Isn't that fun? And speaking of, we've got a 40 Newton force. Did we put a direction? What direction is this ice skating kid going?
North.
Okay, so if the acceleration is pointed north, the kid's going to go north. And that's why we should write out north. 40 newtons north. So your answer for force needs to have direction because it's a vector quantity. I'm going to take 2 seconds to just search again.
2 seconds.
Is this the quest? No, that's module 11 quest. Module 11. There's seriously not a module 10 quest like hanging out somewhere. Very strange. I was done with a whole pile of papers. Tell me you're not filming this. Somebody turn off the camera.
Bethany, is it home?
Turn off the camera while I lose all the papers. Okay.